Before we begin with the bulk of today's lecture, I would like to revisit a definition that you may not have learned in functions, but is crucial to our ability to solve exponential and logarithmic equations, which is a topic that we sort of brushed over last week. In today's lecture, we are going to go into these topics more in depth and see how logarithms are a powerful tool for solving exponential and logarithmic equations. So the first thing that I want to mention is that a function, recall, a function is an assignment of elements in a set, which is called the domain, to another set, which is called the codomain. Okay? Not to be confused with range. Range is the set of images of elements in the domain. So for example, we already know functions like f of x equals x squared. Its domain is the real numbers, and you put in a real number, you get out a real number. Okay? The codomain in this case is still the real numbers. Right? Now, you may be saying, oh, no, hold on. This function only maps to the positive numbers, right? Well, yes, the range of f is the numbers from 0 to infinity. Not to be confused with the codomain. The range is always a subset of the codomain. All right? That's how you should remember. This is not what I wanted to go through. What I wanted to go through was a special type of function. So let me just add here further. Such a function, f, is called injective, or one-to-one, if it satisfies the property that f of x1 equals f of x2 implies x1 equals x2. Now, all this may seem like a big bunch of mumbo-jumbo to you, but I assure you that everything that I'm saying here is stuff that you've seen before. So let's think about what this statement means. This statement says, if the value of my function at one point is the same as the value of my function at another point, well then those 2 points must be the same. Let's think of an example function. So here I'm going to draw y equals x. And I'm going to tell you y equals x is injective. And in fact, any other line with non-zero slope is an injective function, because if f of x1, so some point here, f of x1 is equal to f of x2, so here's x1, here's f of x1. Now it's obvious from the image, but let's say there was another point here that had the same y value, then the x values must also be the same. Right? Maybe you should think of a function that is not injective. Maybe that's more illuminating. So I want you to try and think of that. A function that is not injective. All right, we've already covered one today. It's x squared. So as you can see, x squared does not satisfy this property because I can pick two values, x1 and x2, that basically have the same height. So here is y equals x squared, and they have the same height. So here is f of x1, and it's also f of x2. But as you can see clearly from the picture, x1 is not equal to x2. Thus, this function is not one-to-one. Okay? Loosely speaking, we can apply something that is very similar to the vertical line test to determine whether a function is one-to-one. This is called the horizontal line test. So I will state it without proof here, but hopefully it's intuitive that, fact. I wanted to write fact and I wrote H. So the horizontal line test So it's the horizontal line test is literally like you get a function and it passes the horizontal line test if every horizontal line only intersects the function once. So as we can see here, this horizontal line only intersects the function once, and the way I've drawn it, I've drawn the function in such a way that every other horizontal line that I draw will only hit the function once. So the fact is, if a function passes the horizontal line test, which I'll write HLT, it is injective. And perhaps now we can begin to qualitatively look at the functions of interest in this lecture, which are exponential and logarithmic equations. And we are going to determine whether or not they are injective or not. So here we go. I want you to draw for me a generic exponential graph. And by generic, I mean like really, really general. So I want you to draw what does y equals b to the x look like. And then similarly, draw on another axis, what does log b of x look like? Remember, log b of x is the inverse of b to the x. So I will draw mine on one big axis to further demonstrate the inverse relationship. Let's do this one in blue. So hopefully you got this. Okay. Some key points about this are that there is a horizontal asymptote at y equals 0. It passes through the point 0, 1. And it also passes through the point, this is 1, 1b. And this is because if you put a 1 in the x, you get b, right? So b to the 1 is equal to b. Obviously, the inverse is just going to be a reflection about the y-axis. We talked about this briefly last lecture, and we found that it should look something like this. So I've tried to draw it so that it's somewhat symmetrical about this line right here. Okay, which is of course y equals x. Alright, and the things that you should notice, of course, are that there is a vertical asymptote here. Let me just make sure you can see that. Okay, there's a vertical asymptote at x equals 0. It passes through the point 1, 0. And the sort of image of this point through the reflection is, of course, b, 1. You literally flip the x and y axis if you want, you flip the x and y coordinates if you want the inverse image. And that just corresponds to the fact that log base b of b is equal to 1. The power that I need to raise b to in order to get the power that I need to raise b to in order to get b is 1. The answer is the exponent. Okay? Alright, so that being out of the way, let's check whether these functions are injective or not. Well, visually, the exponential function is injective because it passes the horizontal line test. Look, every horizontal line that I draw here will only pass through it once. It's obvious that it passes the horizontal line test here. Maybe you'd be a little suspicious here, but you could really think about it, and you would see that as you're going here, this function is always increasing. Therefore, it could not possibly fail the horizontal line test because it's always just increasing, increasing, increasing. Similarly for this one, this function is also always increasing, and therefore it too will pass the horizontal line test. Therefore, we have the fact. Now, this is an important fact for what we're about to do. However, I do not require you to memorize it, only its consequence. Sorry, I wrote in green. I probably shouldn't have done that, but here we go. B to the x and log the x for any b greater than 0 are injective or one-to-one functions. Okay, and recall, what does injective mean? Injective means that f of x1 equals f of x2 implies that x1 equals x2. Okay, so now I have spent, over 10 minutes discussing injectivity, a sort of esoteric, abstract term used only by the elite mathematicians to describe certain types of special functions that no one else seems to be interested in. And the reason why I did that is because in school, they're going to sort of do all of this work that I did here in about 2 seconds. They're not going to explain any of the reasoning that they use to justify any of the manipulations that they do. So perhaps you've already solved exponential equations of the form 2 to the x is equal to 2, for example, 16. And then you note that 16 is equal to 2 to the 4. And then you say, aha, 2 to the x is equal to 2 to the 4. Well, it just looks like x is equal to 4, right? Because if x is equal to 4, then we're done. Aha, so you would say x is equal to 4. In other words, you can sort of ignore the base, and then you just like look at the exponents. In other words, you match the exponents. Okay, well, who gave you the right to do that? Like, why are you able to do this? Like, of course, you can look at it and say, aha, 4 is a solution. But how do you know 4 is the only solution? And you can't say common sense dictates so. That's not a valid mathematical argument. For example, what about this? If I write x squared is equal to y squared, does that imply that x is equal to y? No! I could have x equal to 2 and y equal to negative 2. And then x squared is equal to y squared, but it does not imply that x is equal to y. 2 is clearly not the same as minus 2. Therefore, injectivity is the property that allows us to match the exponents. Okay? So this is what the whole lecture is going to be about. Using the property of injectivity in order to solve exponential and logarithmic equations. So let's recap what injectivity gives us here. We're allowed, because we know that the exponential and logarithmic functions are injective, we can confidently say that if sort of b to the x is equal to b to the y, then x equals y. And x and y, I put them as like numbers or variables here, but they could really be entire expressions. So for example, if I said b to the x squared minus 1 equals 2x, right? Then I could confidently say that x squared minus 1 is equal to 2x. And then from here, I could shift the 2x to the other side and then solve for x. Similarly, we're allowed to do this with logarithms because logarithms are also injective. Therefore, I can say if I know log b to the x equals log b to the y, then x equals y. And again, these two can be expressions. Okay? So let's go ahead and do some examples here. We'll start off with some simple ones, sort of questions that you may have already seen before in grade 11, and then move on to some more complex ones that will require us to use logarithms. So the first one is 2 to the x plus 2 minus 2x equals 24. Go ahead and see if you can do this. Alright, so the first issue here is that we don't have something like of the form 2 to the x here. We have 2 to the x plus 2 minus 2 to the x. Remember that you cannot subtract the exponents. The rule is not a to the b minus a to the c equals a to the b minus c. This is not correct. Okay. So if you did that, make sure you erase this move from your vocabulary. Instead, notice that each of these has a 2 to the x in it. If it's not obvious enough, I'll rewrite this as 2 to the x times 2 to the 2. Remember, that's all that's going on here. We are multiplying 2 x times, and then we're multiplying it by another 2 times. So 2 to the x times 2 to the 2 minus 2 to the x. Look, we can factor this. So we get 2 to the x times 2 to the 2 minus 1. And incidentally, that is equal to 3. Meanwhile, we're just going to carry over the 24 to the other side. And notice that 24 is equal to 8 times 3. So we'll divide both sides by 3, and we'll get 2 to the x equals 2 to the 3, which immediately implies x equals 3. Okay. So the tricky part here was knowing to factor this. So once you've got that, all the problems that look like that, which are most of the problems in the textbook, will become very easy. Alright, now let's see a case where we cannot use this simple trick of equating the exponents. So, actually, maybe we'll do one more. We'll do one more that's a little more complicated. Okay. So why don't you go ahead and try this one. 2 to the x squared equals 32. Sorry, equals 32. 2 to the 4x. Go ahead and try that. Alright, so the first thing that you want to do is make sure that both sides are of the form 2 to the something equals 2 to the something. Number. We don't have that here. We have a 32. And I hope you know that 32 is equal to 2 to the 5. Right? So, we're going to turn this into 2 to the 5. Then we'll use our laws of exponents. We can add together the exponents here. And that'll give us 2 to the 4x plus 5 equals 2 to the x squared. Now we can just equate the exponents, again because of injectivity, and then solve for x. Look at that, we get a quadratic. Quadratic's the good old thing that you can solve hopefully very quickly by now. And our two answers are x equals 5 and x equals -1. So as you can see, these exponential functions, they can have, these equations, they can have multiple solutions. However, the key thing that allows us to solve them is that we can equate the exponents if we get into the form 2 to the something, 2 to the something. Next up, we're going to try the question where we're going to need logarithms. So before we do that, I just want to remind you of the key fact that we need to use, that log to the base b of some other number c, or actually, no, we want to take log to the base b of b is equal to 1. Remember, the exponent that I need to raise b to in order to get b is 1. Okay, remember, the answer is the exponent. So here's our question. 225 times 1.05 to the x equals to 450. Perfectly reasonable exponential function, and also a perfectly reasonable solution. So let's see how we're going to do this. We need to solve for x, so it makes sense to try and sort of isolate x as much as possible. To do this, we'll divide both sides by 225. Okay. And I believe if you go ahead and do the work, 450 over 225 should be 2. Okay. Now, let's try and use our key fact here. If we want to get rid of the 1.05, then what we can do is we can do log base 1.05 of 1.05 to the x equals 2. Now, what will this do? Remember, by our law of exponents, we have, laws of logarithms. If you have like a to the c up here, this is the same thing as c log b a. So once we do this, we can sort of bring the x down here, and because of this rule here, the log 1.05 will cancel out. Now, of course, you can't just do it to one side, you have to do it to both sides, so that's the payoff. So log 1.05 of 1.05 to the x equals log base 1.05 of 2. Using our law of logarithms, we can bring the x down. Then this becomes nothing but 1. And you just simply get that x is equal to log 1.05 of 2. So if you're not happy with that, you can always calculate it using your calculator. You would press the log button, the one with the 2 boxes, and just type in 1.05 to evaluate it, and you get something like 14.2. Okay. So that is the way to solve exponential equations that cannot be solved in our normal way. Usually you know to do it this way when A, there's nothing else you can do, or B, when the numbers are messy. Usually if the numbers are messy, it indicates that you cannot do it the nice way. So now let's go through a challenging problem with these log equations. We want to show the following. If log A of 2 is equal to log B of 8, that implies that A cubed equals B. Alright? So this one is a little bit challenging. First, what we're going to do is we're going to look at this question and see what relations we can draw from it. Where's the A cubed coming from? Where's the B coming from? And I think you immediately see that 8 is equal to 2 cubed. And so maybe this is our lead. Maybe this is the way we need to go. Right? So here's a hint. When you don't know what exactly you need to do, just label your unknown as a variable. So we're going to call this thing, this value, log A2 and log B to the 8, x. We can do that because we know they're the same thing. Right? Now let's try and rewrite each of these in exponential form, but this time involving x. So in this question, in this part, we are saying A to the x is equal to 2. And this one we're saying B to the x equals 8. Right? So now where do we go? Try and see if you can figure it out from here. Alright, so if you notice, 8 is equal to 2 cubed. Right? And this is 2, right? A to the x is equal to 2. So that means that we can substitute in A to the x in here. And we get that. Right? Next, we're going to use this. Right? We can switch the way that they are, the exponents are raised. Right? And the reason why is because this becomes a to the 3x, which of course is the same thing as a to the x, or a to the 3 to the x. Right? Now, injectivity does wonders for us here, right? The problem is immediately solved due to injectivity. You take two numbers and you raise them to the same power, and now you know that the numbers are the same. Are the bases necessarily the same? And the answer is yes, they have to be. Okay? So, now what we're going to do is just simply state that, therefore, B is equal to A cubed. Right? So that pretty much covers everything I wanted to do with exponentials. Let's now move on to the more trickier logarithmic equations. I say trickier, but they're really just the same. The only catch is that you have to, instead of using exponential laws to simplify your expression, you have to use the logarithmic laws. And sometimes people get confused. So I'll give you some problems and hopefully try and sort out all that confusion before you even start tackling the homework. So let's start with this one. Log base 2 of x plus 3 plus log base 2 of x minus 3. Right? Equals 4. Alright, so try your hand at that, see what you can do. So the first thing that you want to do is use your laws of logarithms to factor this out as so. So here we're using the law that log A plus log B equals log AB. I didn't write the base down, but it's okay. And the 4 here. Continuing on, what do we get? We get log of... Okay, well, actually, let's think about this for a second. Let's think about this. Suppose I wanted to get rid of the logs here. What would I have to do to both sides in order to remove the logs? The answer is exponentiation. I would have to raise both sides to the power of 2. And the reason is because log and the exponential are two inverse functions, right? So if I do exponential and then log, it cancels out, and if I do log and then exponential, it does cancel out as well. The reason why I have to put a 2 is because the base here is 2. Right? So it is a general fact that 2, or in general, b to the log b of some number x is just equal to x. Okay? And to see that, let's just think for a minute about what log b to the x means. So let log b to the x equal y, then we know that b to the y is equal to x. Right? And therefore, if you just look at this situation right here, right, this thing immediately evaluates to x because y was log to the b, log of b to the x. Right? So the exponential and the logarithm, they cancel each other out. So this is equal to x. Alright, so now that we got that out of the way, we can sort of bring down the exponent, the thing in the log, and we get this. Okay, 2 to the 4 is 16. Then you expand this out, x squared. Okay, you should notice that this is a difference of squares. Right, x plus 3 times x minus 3 is equal to 16. Bring the 16 over to one side, and you get x squared minus 25 equals 0. X plus 5 times x minus 5 equals 0 implies that the answers are x equals to 5 and negative 5. There's one issue. The issue is this. We don't know, these are the answers that we got algebraically, but we don't know whether they will actually work. Because remember, with logarithms, unlike exponentials, the domain of the logarithmic function is only the positive half of the real line. Right? It's only everything from here on. So that might be a problem. So what we need to do, I'm going to put a big warning here, is that after every log equation, check your answers. And this will help you spot any domain problems immediately. Now you can't substitute it back into here. You have to substitute it back into the original thing. So I want you to go ahead and substitute 5 and negative 5 and make sure that both those numbers work just fine. You'll probably notice that negative 5 doesn't do the trick because if you put a negative 5 in here, you get a math error. Because remember, log cannot take a negative number. It always has to take in a positive number. If you put a negative 5 here, you get a negative 8 in the log. Therefore, the only solution is this one. Okay. A little bit tricky there. Let's do another one for more practice. So let's see. Alright. So that was sort of like the basic prototypical example of a log equation. To get another one out there, let's try and do one of these. Oops, I don't want to use bright red. Pretty sure this is fine. So let's just do log 4 squared minus 1. Log 4, 2 equals 2. So try your hand at this one. Alright, so the first thing that you do is use your laws of logarithms again. So you get 2x squared minus 2. Then you recognize that the base here is 4, so if you raise both sides to the 4, the log disappears. You get 2x squared minus 2 is equal to 16. Okay? To finish that off, all you need to do is write down 2x squared equals to 18, which means x squared equals 9, and therefore x equals to plus or minus 3. Then, again, double check your answers. If you put in a 3 here, you're fine. If you put in negative 3 here, you're fine. So actually both of these are answers. Right. Next, we're going to move on to some more trickier ones. So as you can see, the basic idea behind solving these log equations is not too difficult. But making sure that you get all the details right and check your answers, that's where you can lose marks very quickly and easily. So the next question, we're going to have a system of equations. We call the system of equations has some number of variables, in our case 2 variables, and 2 equations. We are looking for a pair x and y that satisfy the system. So in our case, the system is y equals log 5x plus 4, and y equals 3 plus log base 2 of x minus 1. And we're trying to solve the system. So see if you can do anything with this. Sorry, I should put a 2 here. Alright, so assuming you tried it now, let's go ahead and equate the 2 because we see immediately that they're the same thing. So that might be a lead to go off of. Equals 3 plus log 2. Okay, now let's bring both log expressions to one side so that we can use our laws of logarithms. Then dividing, you get log base 2 of 5x plus 4, all that over x minus 1. That's 3. Great, now this becomes just your typical run-of-the-mill exponential, logarithmic equation. You bring everything to the power of 2. Well, 2 to the 3. Then you can cancel out the log in the 2. You get 5x to the plus 4 over x minus 1 equals 8. And then you can just solve this, your typical way. So you get 5x plus 4 equals 8x minus 8. You do some shuffling around, and I believe you get x equals 4. Yeah, you get x equals 4. All right. So that was our pair, right? We found 4. Now we need to find y, right? We're not done here. So you plug in 4 into here and check what that gives you. So if you plug in 4 in here, you get 3 plus log base 2 of 3. Very ugly number. This does not have a nice form to write it in, but that's the answer. So y is equal to 3 plus log 2 base 3. Right? Okay, so next we're going to try a sort of strange one. It's going to look weird, but I want you to really give it your best shot because if you get through it, it's actually not that difficult. It's just conceptually, you need to be on your toes. So let's see, log base 2 of log base 4 of x equals 1. So go ahead and try that. All right. So first step, kill the logs. Raise both sides to the power of 2, and then you get log base 4 of x is equal to 2. Do the same thing. Raise both sides to the power of 4, and then you get x equals 16. That's literally it. That's the solution. Okay? There's no problems because if you put a 16 in here, you always get a positive number. So that's pretty much the answer. Very nice, quick and easy. All right, final question of the day. Actually, no. Final question for the log equations, and then we're going to move on to a little word on graphing, and then we're going to be done. So we do log base 2 of a plus log base 2 of b equals 4, and the question is find all possible values for a and b that are integers. Remember, Z stands for integers. Okay, so give that one your shot. Okay, Now, what I want you to do first is, of course, apply your laws of logarithms. Okay. Then you raise both sides to the power of 2. You get AB is equal to 16. So, what numbers that you multiply together will give you 16? Maybe easiest to write down a list of factors for 16. So 16, you break it down, it becomes 1. The factors are 1, 2, 4. 4 times 4 is equal to 16. So you get 8 and 16. So really, you pick A and B to be any of these pairs, or A and B both equal 4, and those would provide a solution to this equation. So the answers are just all the pairs of numbers, of integers, that multiply together to give 16. And that's it. Those are our equations. So hopefully by this time, you found the procedure pretty routine and straightforward. The more you do it, the more it becomes sort of second nature, and then even the most difficult, strange, oddly worded questions just became a simple application of the technique, right? So that more or less covers everything that I wanted to do in advanced functions. The only thing that I'm going to mention is a word about graphing these logarithmic functions. Now, what I'm going to show you here is going to be so similar to everything that you've done in the past that it might seem useless to repeat it, but I think it's worthwhile just to see 1 or 2 examples worked out. And that's how to graph logarithmic functions. So again, you know, we get functions of the form a times f of b times x minus c plus d, and we know, of course, that this is horizontal stretch, this is a vertical stretch, horizontal translation, and vertical translation. All old stuff that we've done plenty of times in this course, and even before. So, with that being said, we are going to now consider the case where f of x is a logarithmic function, i.e. log b of x. Right? So, as we saw, the exponential function b to the x looks like this, b to the x, whereas the logarithmic function looks like this. It is the inverse. It is the inverse function. So this is log b to the x. And we get 2 key points, namely the x-intercept, which is at the point 1, 0, and this point around here, which is b, 1. b, right? And that just comes from inverting the correct points on here. So, if we're going to graph this, all we really need to do is focus on what happens to these 2 points. Pretty simple. So let's just do a quick example. And of course, the key thing that you want to keep in mind is the vertical asymptote and the overall shape of the graph. It looks like a little half of a V, curly V. All right. So for example, let's do -2 log 3 of 5x minus 1 plus 8. Okay. Actually, maybe we'll turn this into something a little more nasty. Let's do 5x plus 10. Alright, so of course, in order to start with this, I want to convert it into my regular form. So we get -2 log 3 of 5 times x plus 2 plus 8. Okay. So log 3x, looks, of course, like this, and it passes through the point 1, 0 and 3, 1. To apply these transformations to it, let's first consider the stretching. So when we're stretching horizontally, we're squishing everything by 1/5. Okay. Maybe you'd like to do the vertical stretching first. That's fine as well. I'll do the horizontal stretching first. So if you squish everything by 1/5, this point 1, 0 gets sent to 1/5, 0. 1/5, 0. And this point here is going to get squished horizontally, so 3/5, 0. 3/5, 1. So it's going to get moved here to 3/5, 1. Okay? 2 points right there. Then we need to take care of the vertical stretching. So first notice that there's a vertical flip, so we'll have to flip this thing in the x-axis. Let me just do that here. it's going to look like this. Nothing changes, it's just flipped in the x-axis. So this point is still 1/5, 0. But this point, of course, this mirror image is going to be 3/5, -1. 3/5, -1. It just, it switches to the negative. Next, we're going to do the vertical stretching. So that just means that this point here gets doubled, right? Which means it's going to get sent to 6/5. So it gets stretched a little. Maybe I'll do it in red. Stretch this thing a little bit, but keep in mind that it still has to pass through that point 1/5, 0. Okay. So it gets stretched down to 6/5, -1. Okay. Oh, sorry. My bad. You're doing a vertical stretch. So the vertical component, the y component, gets stretched by 2. So it should be actually 3/5, -2. All right. Just making sure I haven't made any other mistakes. Okay, that seems about right. Right. So now all we have to do is take care of all the translations. That should not be too hard. You just have to calculate them. So if you take the point 1/5, 0, shift it left by 2 and up by 8, you get, well, the y coordinate is going to be, well, maybe I should draw the axes first. So 1/5 minus 2, just make sure you can read that. Yeah, so 1/5 minus 2 is equal to, well, 2 is equal to 10/5, so this is just -9/5. So this point gets sent to -9/5, and the y coordinate is 8. So let's put here 8, -9/5, and that's 1 point. Right. This point here, 3/5, -2, gets sent to, well, 3/5 minus 2 is equal to -7/5. So -7/5, let's say it's like here, -7/5, and then the -2 gets bumped up to 6, right? Because -2 plus 8 is equal to 6. So we get these 2 points here, right? And then our graph roughly looks like this. Okay. Now the only thing that we need to care about now, if you want, you can calculate the y and x intercepts. I'm not going to require that of you. I don't think it's necessary. The only thing that's left is to figure out where that vertical asymptote went. I really do want you to figure out where that vertical asymptote goes, but it's easy to find because it's just going to get shifted by the horizontal translation. So the vertical asymptote is now no longer at 0. It's going to be, at x equals -2. So here, let's call that -2. Remember, -2 is equal to -10/5, so we're all good. That is going to be our vertical asymptote. Okay, so VA at x equals -2. And pretty much every example with logarithmic graphs is done this way. You just take the parent graph, do the transformations like you did for every other function. Maybe I'll do one more example if it's beneficial, but I'll do it very quickly. And it will really just be like a practice one for you to try and get your head around this. Make sure that all the concepts are still there. Okay. And I'm going to do all the steps on one graph, so it's going to get a little bit messy, but I'll use different colors to hopefully make it a little easier to see. So let's do log 2. Let's do 3 log 2 of -4 x plus, let's do 2 plus 6. Let's do minus 6. Right? So first thing again, you want to convert it to your standard form, which means factoring out the -4. X minus, and that's because -4 times -1/2 is equal to 2. Then, once you've done that, you can start graphing. Here are my axes. Okay. Drawing the parent graph is not a big deal. You just have to do that. This is, of course, 1, 0. This is, I'll just call it that. We'll call it the point 3, 2, 1. Okay. Then you want to do the vertical and horizontal stretching. So this time I'll do the vertical stretch first and then the horizontal stretch. Vertical stretch is by 3, so this point gets tripled in height which means it's going to get sent to 2, 3. So maybe you just draw it a little bit longer. Here's the point, 2, 3. Okay? The shape doesn't really have to change that much. Then we have to do this, which is a horizontal squish of times 4. So this point is going to get sent to 1/4, 0. Remember, we're only playing around with the x coordinate. This point is going to get sent to 1/2, 0. So let's say 1/2 is around here. Sorry, 1/2, 3. 1/2. You only play around with the x coordinate when you're doing horizontal stretches. Vertical asymptote stays the same. All right. Now, let's see. Oh, we have to take care of that negative, right? So we're going to flip it in the y-axis. So vertical asymptote is still going to be 0, but now we have negative 1/4, 0, and negative 1/2, 3. All right. Then to finish it off, you just take care of your translations. So let's see. Here, we're going to shift it right by 1/2 and then up 6. Maybe I'll do the final one in blue. So if we take the point negative 1/4, 0 and shift it, so right, so x plus 1/2, we're going to shift right by 1/2, and we're going to shift the y down by 6. Then we get -6 and 1/4. So let's just plot that. 1/4, and let's say -6 is over here. So this is -6. This is the point. 1/4 -6. The other point, which we do the same thing to, is negative 1/2, 3. Then we perform this operation. Go sent to negative 3 and 0. So let's put that down. 0, negative 3, let's just say it's around there. Okay. So that's what our graph is going to look like. It's going to look something like that. Okay. Just imagine taking those 2 points and just shifting them down there. I know the scale is way, way, way off, but it's okay. These are rough sketches. The last thing you want to take care of is the horizontal asymptote. The vertical asymptote. Now the vertical asymptote was at x equals 0. Therefore, when you shift it right by 1/2, the new vertical asymptote is at 1/2. So here's 1/2, dotted line. Okay, and we put VA equals 1/2. The blue one is the final graph. So hopefully you were able to follow along all those steps. But that's the gist of logarithm graphing. With that being said, we are now done with advanced functions. Next lecture will be our first calculus lecture. Very exciting. The sections of the textbook that correspond to all this are pretty simple, and I've really taken the worst of it. So, you know, if you understood everything that I did here, if you're at least able to follow along, the questions in the textbook should not be that much more difficult. Again, everything here is about practice, so the more you practice it, the easier everything will become. Okay, I think I'm going to end it off there today.